Hello class. Today is going to be our second to last lecture, so let's get started. Okay. So today is lecture number 29. We're going to cover stuff that's in chapter 15 from pages 408 to 413. For next class, read 421 to 434, and your homework will be due on Friday. Okay. So today is going to be a damped harmonic oscillator. So, objects in the real world don't behave like the simple harmonic oscillator we saw last class, right? It's been sort of a theme of this class that we study the simple case, and then we talk about some sort of more complications or more realistic scenarios that could be brought into play, right? Most of you are engineering majors and you want to go out and design and build things in the real world, and so presumably you would like those things to work correctly in the real world, which means you have to take into account real world complications like friction, drag, objects that aren't perfect shapes, etc., etc. So now that we've studied the simplest case for harmonic motion, the simple harmonic oscillator, we're going to put on top of that one more complication, which is drag. Right? And when we have a harmonic oscillator where the movement of that oscillator is opposed by some other force, we call that a damped harmonic oscillator. So just to draw our little picture of a harmonic oscillator again, we have some anchor point, we have a spring, we have some mass attached to that spring, and then that mass is displaced some distance from the equilibrium, which we define to be x equals 0. So we've got the force of the spring pointing in one direction, and we've got the velocity of the object. If it's displaced in this direction, it's going to go that way. And now, if we want to consider the force of drag, we're going to have another force coming into play, which is going to be pointing in the opposite direction of that velocity. Remember, drag is always defined to be pointing in the direction opposite the object's direction of motion, right? That's how drag works, much like friction. So we want to write the total forces in the x direction, right? That is negative kx, which we get just from our Hooke's law for force for a spring. And now we have to add a negative bvx, right? Where this b, that's going to be the drag coefficient, right? And that depends on the shape of this object, how viscous the fluid is, and several other factors, right? And this Vx, that is a vector, even though I didn't put the vector sign on it, because the negative sign for which direction the velocity is in is pointing, or is inside this V. Okay, so that V can be positive or negative. Now we're going to use the same method as before, except it's going to be a little bit of a longer calculation, which will be really good practice for the kind of stuff you'll do as you progress throughout your career as an undergraduate STEM major, right? These kinds of calculations, though lengthy, are the ones that are more similar to the ones you'll actually be doing if you're doing like a research project or working in an internship or something like that, right? If you go into your engineering job or internship, they're not going to say, okay, here's 20 plug and chug problems, please solve them, and then hand them in by the end of the day. They're going to say, here's a more difficult problem, maybe here's some people to work with, and now you work on this problem over the course of some period of time, right? And depending on what you're doing, that might be a calculation sort of similar to this, at least in mechanics. So, like last class, when we talked about the simple harmonic oscillator, we're going to use our Newton's second law and then write the equation of motion for this system as a differential equation. So we get negative kx minus b dx dt equals m second derivative of x with respect to t. So just rearranging this slightly, you get m second derivative of x with respect to t plus drag coefficient first derivative of x with respect to t plus kx equals 0. Okay. So maybe I should. It's always so difficult to tell. No, I'm just going to leave it alone. It's always so difficult to tell if you guys can really see well before I go and watch a little bit on my computer before I upload it. But hopefully this looks okay. Okay, anyway. So we have our differential equation here, and it looks just like the one we had last time, except, oh, there's some, yeah, this is correct. Except we have this extra term here. Right? We have this first derivative of x with respect to t. Okay, so what that means is we're going to have to modify our guess a little bit for our guess and test solution of this differential equation, right? This calculation is going to work the same way as the one we saw last class, but now we have an extra term, which means our guess is going to be a little bit more complicated, right? Of course, I'm going to guess the correct answer because I already know it, but this guess that I'm going to guess is one of the standard guesses, right, that you might use when solving these types of equations. When you get to your differential equations class, you'll see that you know, if you're solving a differential equations problem on your own with guess and test, the first guess might not be the correct one, right? You might have to try a couple before you guess the correct one, but that just comes with experience. So the guess we're going to guess is going to be x as a function of t equal to a naught e to the negative c1t times cosine ct, or c2t. So we've got something similar to before. We've got an amplitude, which is given as some constant, times some cosine. Inside the cosine, we have another constant, right, which we're just going to call C2. Before that was the frequency. And we're not putting in the phase, right, that plus delta, because like we talked about last class, if we're looking at just one harmonic object, that phase, that's just the choice of when we start the time, right? That's the choice of origin of the time coordinate. So we can just choose that to be 0. Okay? And as long as we're not talking about more than one oscillator, that phase is sort of irrelevant. Now, the thing that's new, and we did that just to be simple. Okay? The thing that's new is this exponential function here, right? This e to the negative c1t. So just to draw that function real quick, so you're certain you've seen it before. I mean, we've done it a couple times in class, but let's repeat. So exponential decay functions look like this, right? If this is e to the negative x, this is 1, right? I plug in e to the 0 at the coordinate, I get 1, and because I have the minus sign here, I have an exponential decay. Of course, if I had a positive constant, or a positive number up here, it would look like that, right? Okay. So the reason to guess a function that has a cosine, right, the oscillations times this, this exponential decay function, right, the physical intuition for that is that if I have an oscillator and it has some drag, of course it's not just going to go on forever, it's going to slowly be damped or slow down, right? And so this exponential decay function is what's going to take that into account. Okay. So we had that differential equation that we had on the last board, and that had a first derivative of x with respect to position, and it had a second, or excuse me, had a first derivative of x with respect to time, and it had a second derivative of x with respect to time. So we're going to have to take both of those derivatives to get our differential equation. Okay, now the thing that makes this calculation a little more lengthy than the last one we did is that in order to do that differential, since we have two functions of t multiplied with each other, I'm going to have to use a chain rule. Okay, so first derivative. I'm just going to write and then I'll say it. This is going to be difficult to do on this tiny board. Right, these might be the largest equations you've seen so far. But it's nothing scary, as long as you're just careful and you take your time. So I'll skip some algebra steps, but I encourage you to fill them in. Okay. So we take this function, we take the first derivative, we take the derivative of the exponential first and multiply it by the cosine. The derivative of the exponential, right, what happens when we do that is we just bring this constant downstairs, and then that cosine is the same. And then we do the derivative of the other component, as we do with our product rule. And then now we're taking the derivative of this cosine, so we get a negative sign, and this C2 comes from inside the sign when we do our chain rule. Okay? So we get this expression here, and then we factor out that e to the negative C1t, and we get negative a naught e to the negative C1t quantity, this trigonometric function here. Okay? So now we want to do this second derivative. Try and write a little smaller. Okay. So got a little cramped on the right hand side there. And hopefully you can see what's going on. All right. So now we're doing the product rule again, except the two products are this term and this term. Right? We've got that exponential function times these two trigonometric functions added together. So the first thing we do is you take the derivative of this guy, right, and another C1 comes down, the minus signs cancel out, okay, and then we leave this bit the same, and then we keep this bit the same down here, and we take the derivative of this bit. So then this works with taking those derivatives of trigonometric functions, just like it did up here, and we just get now a longer expression. So now we're going to plug those in to our differential equation. I'm just drawing a line so it's neat. So as I said, there's some algebra in here. So it's a long equation, but nothing is too weird. I just take these two derivatives, I plug them into the differential equation I had on the other board, and I simplify, and then I end up with this guy here. Okay? So what we're going to do to this expression is, well, the first easy simplification is we can just divide out by this e to the negative c1t, because that appears in every term, so we can get rid of that. And then what we will do is we'll collect all the sines together and all the cosines together in one form of the equation. So this is yet another simplification of this equation down here. Do over. Okay. So now we have an expression that's just a bunch of constants times a cosine, plus an expression that's a bunch of constants times a sine. Okay. So now there's a little bit of a problem here. Right? We're doing our guess and test solution, so we have to figure out if this is a true equation or not. Right? If you remember from last class, the way we ensured that this was a true equation was we set the constants such that this equation was true, and that made our guess correct, right? So how do we do that here? How do we simplify this guy and find out whether or not this equation can work if we choose the correct constants? Now, if we look at it for a while and we try algebra tricks and stuff, we might not make much progress. But so if we were in class, I would challenge you to try and figure this out. So the question is, we've got a bunch of constants times a cosine plus a bunch of constants times a sine. How can we choose these constants such that we know that this side of the equation is equal to the other side, which is 0? So how can we be sure that these two guys added together is always 0, even though we have a different time function multiplied by each of them? So pause, think. The answer is kind of glib, right? It's just that we take these constants, which we can choose, and set them equal to 0, and we take these constants, which we can choose, and also set these equal to 0, and then we have 0 plus 0, which is always equal to 0. So, what we end up with now is mc1 squared minus c2 squared minus bc1 plus k equal to 0, and 2mc1 c2 minus bc2 equal to 0. So what are the unknowns here? The only unknowns are c1 and c2. M, b, and k are physical constants given from us by our physical scenario that we're studying, right? The only unknown constants that we put in our guess for our guess and test were the c1 and c2. But now we have two equations and we have two unknowns, which is perfect, right? Of course, we know we can solve a system of equations like that. So we'll start with the simpler one, right? And we end up, after we solve this equation algebraically, c1 equals b over 2m. Okay? And now that we have that, we can plug that c1 into the other equation. And we can solve that one. So we get m 4m squared under b squared minus c2 squared minus b squared over 2m plus k equal to 0. Right? So we just took this guy and plugged it into the c1s here, and we get this expression here. So we do a little bit of algebra, which I'll skip over, and we get c2 equal to square root k over m minus b over 2m squared square root. So now we have our correct answer for our guess and test solution to that damped harmonic oscillator, right? We would take that equation that we had a couple boards ago, we would plug in these constants, and then we would have the correct answer. So I'll write that out in full in just a minute, but I just want to talk about one more thing, which is we need a new definition, which is something called the natural frequency, right? Which we write by omega naught. And this is the frequency that that oscillator would have if it was not being damped, right? So if that oscillator existed in a vacuum, right, we would say that the frequency that it oscillated at would be the natural frequency, right? And then any modification from that natural frequency is taken care of by the rest of the elements of the equation. So then we could rewrite this C2 in terms of the natural frequency as omega naught times 1 minus 2m omega naught b squared square root. Okay. So why did I make that substitution? It didn't really make this equation any simpler. Well, a lot of times we change equations around not to make them visually simpler, but to more easily see how certain behaviors arise from that equation. Okay. So we'll see why this is useful in just a second. So I will now rewrite our solution to our damped harmonic oscillator, our x position as a function of time in full, just so you see it. So we have x as a function of t equal a naught e to the negative quantity b over 2m times t times cosine t omega naught, that natural frequency, times the square root 1 minus 2m omega naught under b squared square root. Okay. So the ratio of the mass to the drag constant is what's known as a type of time constant, right? When we have a constant that's multiplied by a time in one of these exponential functions, whether it be a decay or a growth function, that time constant parameterizes how quickly that process takes place, either how quickly that decay takes place or how quickly that exponential growth takes place. Okay? So we call those time constants. And we'll make the simplification t, or rather tau, is equal to m over b, and this is our time constant. So that's a new definition. Time constant. Okay. Now, what we could do is group together, excuse me, group together these two terms here, this a naught and the exponential function, and that we're going to call our new amplitude, which will be a time-dependent amplitude. Okay. So we're rewriting this equation in a more familiar form where we have an amplitude sitting outside of an oscillatory cosine. So what's going to happen here is this guy is going to tell us how big those oscillations are, right, as a function of time. Obviously, if this is a damped harmonic oscillator, it's slowing down, this decreases as a function of time. And then this tells us about the rate of oscillation. So let's draw this. x as a function of time, and then this, of course, is time. So we're going to draw in that exponential decay function, like so. Actually, let's use 3 different colors. Let's be exciting. Let's draw in that exponential decay function. So that looks something like this, right? If this time constant's really, what would it be? If it were really big, right, this would be really slow. So we're drawing one that's really slow, just so you can see the behavior, right? I'm just drawing this a as a function of t here. A as a function of t. So this is what we call an envelope function. I'm going to draw a mirror of it down here. It's very difficult, at least for me. Yeah, it's not bad. Okay. So this is the amplitude of that harmonic oscillator as a function of time. And now, of course, we have these oscillations. So what the function actually looks like is this. We'll start off with some amplitude, right? And that amplitude decays. But we have oscillations within that amplitude. So this is why that amplitude, that exterior function, is called the envelope function, because it forms an envelope within which the actual full function itself oscillates, right? Or has some other behavior, right? In this case, a cosine t omega naught times this stuff here. So if we want to look at the frequency of this equation, we notice that the frequency doesn't change. I still have a constant frequency, right? I have time times some larger constant, right? These are all constants. So this is still a regular oscillation. The fact that a stamp doesn't make these peaks or troughs, the distance between them change as we go along time, right? It changes how often they come, but it doesn't change more as time goes on. That oscillation is still constant. It's just constant at a different rate. And then the thing that does change as a function of time is this envelope, is this amplitude, right? And this makes total sense if you think of something that's oscillating, right? If it's oscillating back and forth and it's being damped by drag, well, that amplitude's going to slowly, as we go through time, get slower and slower and slower. Now it's still oscillating, right, at that same frequency. It's just that it's moving a smaller distance, okay? But the oscillation stays constant. Okay. But now we're going to see something kind of interesting, and it's something we haven't really seen very much or talked about very much in this class, which is different regimes of behavior, right? So we have one equation that describes how this system behaves, but depending on how our constants are chosen, right, or what constants we're given, this system can behave in 3 different physically distinct ways. Okay, and the way we can see that is by looking at what's in the interior of this cosine here, and especially what's underneath this square root here, right? So this is actually the reason that we wrote it like this, so we could easily see these 3 different regimes of behavior, 3 different fundamental types of behavior. So if we look at this square root, there are 3 possibilities. So first what we're going to do is define what's called the critical value for the dampening constant. So that definition is BC 2m omega. Okay, so what if the dampening constant is exactly equal to 2m omega naught? Well, we have 2m omega naught over 2m omega naught simplifies to 1.